So far, the story has been about physical quantities that have a number and a unit. Together, tell us how big or small something is. And we add uncertainty to describe a number's accuracy and precision. Now, let us talk about physical quantities that need more information to describe other than just a number and a unit. To begin, consider this example. A student conducted a survey about customer satisfaction in commuter service at several train stations. He started from the Universitas Indonesia station. During the first half of the day, he traveled 4 kilometers to one of the stations and conducted the survey there. He spent the rest of the day moving another 2 kilometers to another station. The question is, what station did he finally end up? Assume the distance between stations is 2 kilometers. Let us zoom in on the map and focus on this selected area. Even though we know how far he traveled, we can't answer this question. We have no idea where he finally ended up. The reason for this is that, given the scenario, there are 4 possible directions the student could go. First, the student could travel 4 kilometers up on the map to Lenteng Agung, followed by another 2 kilometers to Tanjung Barat. Or he could travel 4 kilometers up to Lenteng Agung and then 2 kilometers down to Universitas Pancasila. The third possibility, the student could go 4 kilometers down to Depok Baru and another 2 kilometers down to Depok. Or, the last possibility, the student could have traveled 4 kilometers down to Depok Baru and returned 2 kilometers up to Pondok Cina. From this, we learn that the direction is important. Saying up and down will take care of this ambiguity. In physics, at least as taught in the IB, any physical quantity is either a scalar or a vector. Scalar quantities can be described completely by the magnitude and the unit. The magnitude describes how big or how small something is, and the unit is the reference. Another type of physical quantity is a vector quantity. To describe vector quantities, in addition to the magnitude and the unit, we also need the direction. This table shows common examples of scalar and vector quantities. Mass, for example, is a scalar because we don't need direction to describe the mass of an object. The mass remains constant regardless of which direction the object moves. Force, on the other hand, is a vector. Force is either a push or a pull. To describe the motion of an object exerted by a force without ambiguity, we must specify in which direction the force is applied to that object. Now, how do we represent vectors? Take a look at this example. A boy lifts a point labeled 1 for 10 meters to another point labeled 2 along an arrow labeled A, as illustrated here in this figure. In this case, this arrow represents a vector that describes the displacement. So a vector is an arrow with a beginning and an end. That is why it is frequently defined as something with a magnitude and a direction. We name a vector with a single letter. In a textbook, the letter is printed in boldface. This is to emphasize the distinction between vectors and scalars, to remind us that vectors are not the same as scalars. The length of the arrow is the magnitude. The arrow in this example is scaled to represent 10 meters, so the unit is meter. What about the direction? The direction is basically the direction of the arrow. The angle formed by this arrow and the x-axis is frequently used to describe the direction mathematically. Let us now discuss the meaning of vectors with the same magnitude and either the same or opposite direction. Vector B here is equal to vector A since they have the same magnitude and the same direction. So two vectors are said to be equal if they have the same magnitude and direction, regardless of where they are located in space. We write B equals A. The use of a boldface equal sign emphasizes that this equality is relating to vectors, which is different from scalar equalities. Two vectors are equal only when they have the same magnitude and the same direction. Now, vector C here has the same magnitude or length as vector A, but it is pointing in the opposite direction. You must agree that if there is any vector that deserves to be called vector minus A, it is this guy. It is this vector C. Vector C is just vector A flipped over, pointing in the opposite direction. So the minus sign tells us the direction that is opposite to the original vector. We write this as C equals minus A.